In today's lecture, we'll be looking at functions, relations and functions, domain and range, determining whether relations are functions, function notation, increasing, decreasing, and constant functions. We will look at the different definitions for a function. A function is a relation in which for each distinct value of the first component of the ordered pairs, there is exactly one value of the second component. Definition 2, a function is a set of ordered pairs in which no first component is repeated. Definition 3, a function is a rule or correspondence that assigns exactly one range value to each distinct value in the domain. Essentially, a function consists of an input and an output. Typically, the input is denoted with the letter X, and the output is denoted with the letter Y. For each input, there is exactly one output. For each input, we only have one value for the output. The domain and range. In a relation consisting of ordered pairs x, y, the set of all values of the independent variable is denoted with the letter x, is known as the domain. The set of all values of the dependent variable, denoted with the letter y, is the range. Example 1, deciding whether relations define functions. Decide whether the relation defines a function. We have f is the set of points 1, 2, negative 2, 4, and 3, 4. Here we have 1 is the input, and that gets sent to 2. The x component is the input, and the y component is the output. We're saying 1 gets sent to 2 with the first point, and the second point says negative 2 gets sent to 4. And the last point says 3 also gets sent to 4. Now, is this a function? To be a function, for each input, there is exactly one output. And that's what we have. 1 has exactly one output, 2. Negative 2 has exactly one output, 4. And 3 has exactly one output, 4. Since this relation has exactly one output, for each input, this is a function. Decide whether the relation defines a function. We have h consists of the points negative 4, 1, negative 2, 1, and negative 2, 0. We'll illustrate if this is a function or not by drawing a picture. Negative 4 goes to 1. Negative 2 goes to 1. So we have no problem so far. But negative 2 also goes to 0. In this case, we have 2 different outputs for negative 2, and therefore, this is not a function. Tell whether the relation defines a function. 3 gets sent to negative 1. 4 gets sent to 2. 4 also gets sent to 5, and 6 gets sent to 8. The domain is the set of all x values, and you can see here the x values are the points 3, 4, and 6. For the range, we have the values of the y coordinate, so that's going to be negative 1, 2, 5, and 8. Now, is this a function? Well, it's not a function because of 4. 4 has 2 outputs, and that disqualifies it as a function. For each input, we can only have one output, and here we have 2. We have an output of 2 and an output of 5. So this is not a function. This is not a function. In part B, 4 gets mapped to 100, 6 gets mapped to 200, 7 gets mapped to 200, and negative 3 goes to 300. The domain is the set of all x values, 4, 6, 7, and -3. The range is the set of all outputs, so we have 100, 200, and 300. In this case, we just have a set of values. The order doesn't really matter for our domain or range. Is this a function? Yes, it is a function. We have one output for 4. We have one output for 6. Even though 7 has the same output, it's still one output. And 300 is an output for -3. We have only one output for each input, and therefore this is a function. In part C, this is the point -5, 2, 0, 2, and 5, 2. Now, is this a function? It actually is a function. We have -5 goes to only one output 2. We have 0 goes only one output 2. We have 5 only goes to one output 2. So we have one output for each input, and therefore this is a function. We might have the same output, but that's okay because there's only one output for each input. What is the domain? The domain is the set of all x values, and in this case we have -5, 0, and 5. For the range, I only have one output, and that's 2. And that's okay. It's just a similar output, but it's only one, so it's still a function. Example 3, finding the domain and ranges from graphs. Again, we already know that the domain is the set of all inputs, so we'll look at all the x values in our points. We have -1, 1, 5, 0, and 4. So these are all the x coordinates that we can possibly have, and that's our domain. Again, the order doesn't really matter as long as we list all the values. For the range, it's the y component. We'll have to list all of the y components from our picture. We have 1, 2, 2 is repeated twice, so we'll just mention it once. A -1 and a -3. This is all our different values for the output, and that is our range. In part B, we want to find the domain and range of a graph that doesn't have finite points. There's infinite points on this elliptical curve. And so what is our x values? Well, our x values are all of the possible coordinates that we can have for this ellipse. Now, if I look at the graph, I can follow all of the x values on every single point of this graph. But there's going to be infinite values, so we need to state it as an interval. The farthest x that we can have is -4. The farthest x that we can have to the right is +4. So our domain is square bracket -4 because that's included. -4 is a possible value of x. And then we go all the way to +4, and that's also a square bracket because we can possibly reach 4. It's included. For the range, we have something very similar. The lowest value of y that we can get is right here. That's a -6, so we're going to use a square bracket. And the highest value of y that we can have is a +6. We're going to use a square bracket again because it's included. The domain is from -4 to 4, including the endpoints, and the range is from -6 to 6, including the endpoints. In example C, the domain of the function is the set of all x values, And if you look at our graph, it goes forever to the left. So the domain would go to negative infinity. And it does also go forever to the right. So our domain is from negative infinity to positive infinity. For the range, it's how far down the graph goes. And the graph goes down forever towards negative infinity. And it goes up forever towards positive infinity. And so our range and our domain are both the same, negative infinity to infinity. In part D, let's find our domain. The domain is how far the graph goes to the left, and it goes forever to the left. It goes forever to the right. The domain is negative infinity to positive infinity. For the range, however, it doesn't go down forever. It stops right here at -3. The range goes down to -3. We're going to use the square bracket because it actually reaches -3. But it doesn't stop when we go upwards. It goes up forever. So our range is -3 to infinity. And remember, you always put a square bracket if it's included. And for infinities, we never use square brackets. We always use parentheses because technically we cannot reach infinity. Just a small note, we have an agreement on the domain. Unless specified otherwise, the domain of a relation is assumed to be all real numbers that produce real numbers when substituted for the independent variable. The vertical line test. If every vertical line intersects the graph of a relation in no more than one point, then the relation is a function. This is a quick test to determine from a picture if a graph is a function or not. If I look at example 4, and I draw vertical lines at every point on the graph, you will see that it only intersects once. Since it only intersects once at every single point, this is automatically a function. Using the vertical line test is a quick and easy way to determine from a picture if a graph is a function or not. In part B, I just need to find one example, and I found one right here. This vertical line touches the graph at more than one point, so this is not a function. We only need to find one example, and this disqualifies it as a function. We have 2 points that a vertical line can intersect. Part C, if I draw vertical lines here, 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 or here, I will never be able to intersect this at more than one point, and so this is a function. In part D, similarly, we cannot find a vertical line that intersects more than once, so this is a function. Every single vertical line intersects just once, and therefore this is a function. In example 5, determine whether each relation defines y as a function of x and give the domain and range. In part A, you can tell this is a line with a slope of 1 and a y-intercept of 4. If we were to graph this, the y-intercept would be 0, 4, and we have something similar to a line with a slope of 1. And by the vertical line test, this is obviously a function. Now for the domain, we can see that it goes forever to the left, so that's negative infinity to infinity. And for the range, we do not have a restriction on the range because for each x that we have, y is just 4 more than that, So the range is very similar, negative infinity to infinity. And if you look at the graph, it also goes down forever and up forever. So our range is all real numbers. For part B, we do have a function. And you could determine this by plotting points. And you will get a graph that's similar to this. It looks like the square root function, but slightly different. And you can do this by plotting points, by plugging a number, calculating it, and you'll be able to get something with a similar shape. This is a function with the vertical line test. And the x here does have a restriction. When we're taking the square root of a number, it must be greater than or equal to 0. So we'll set 2x minus 1 greater than or equal to 0. That is the restriction on x. We have a restriction because we cannot take the square root of anything less than 0. We'll solve for x by adding 1 to both sides. 2x is greater than or equal to 1. Divide both sides by 2, and I have x is greater than or equal to 1/2. This implies that my domain has to be 1/2 or greater, and therefore my domain is a square bracket 1/2 comma infinity. For the range, well, the range is all the possible y values, and the square root of any number has to be greater than or equal to 0. The range is all of the y values that are greater than or equal to 0. And this implies that our range is from 0 to infinity. Again, the square root, the smallest it could be is 0, and it can be as big as we want. So the range is from 0 to infinity. In part C, we have a graph that looks like a sideways parabola. And if I were to plot points, I would get something like this. Now, by the vertical line test, this does not qualify as a function. This is not a function. The x is equal to a squared term, and therefore can only be 0 or greater. So we have x has to be at least 0 or more, and that implies that our domain for the x must be a square bracket 0 to infinity. For the range can be anything it wants, right? We can have whatever we want for y, and that would be an acceptable answer. And if you look at the graph, it also shows that as well. So we can go down forever and up forever for our sideways parabola. So our range would be from negative infinity to infinity. In part D, we have the relation y is less than or equal to x minus 1. In order to figure out if this is a function or not, I'm going to draw a little sketch. Now, for this one, we could pretend this is the equation y equals x minus 1. And that's easy to graph. We just go down to the y-intercept, 0, negative 1. And then we have a rise of 1 and a run of 1 because our slope is 1. And that's by looking at the number in front of the x. So our slope is 1, or I can write it as a fraction 1 over 1. This is my rise, and this is my run. And that gives us our graph, y equals x minus 1. But we want to graph y is less than or equal to x minus 1. I know we're going to use a solid line because of the equal sign. Now, where are we going to shade? Let's pick a test point. And I typically pick 0, 0, something off of the line, and that is the easiest one that we can think of, 0, 0. And we'll plug that into our original relation. Is 0 less than or equal to 0 minus 1? And that is false. That implies all of the solutions on the opposite side of that point. So I'm just going to shade on the opposite side of the graph. There is our relation. Now this is clearly not a function. This is not a function because I could pick any point in the shaded region and automatically will fail the vertical line test. There's many points that the vertical line test would fail. In this case, it is not a function. Now, what is our domain? Our domain, if you look at the graph, well, it goes forever to the left, forever to the right. So that's negative infinity to infinity. For the range, same thing. We have negative infinity to infinity. It goes down forever, goes up forever. So that is our range. In example E, for each input, there is exactly one output, y, and so this is actually a function. Now in the future, we'll be able to graph these, but for now, just realize for this function, we have a unique output for each input because the operation 5 divided by a number minus 1 is always going to give us just one value for y as our output. So this is a function. In the denominator, we do have a restriction. X minus 1 cannot be equal to 0. And that means we have a restriction on our domain. If I solve this for x by adding 1 to both sides, I get that x cannot be equal to 1. And if you were to graph this on the number line, everything is okay except at x equals 1. That means our solution would be the following. We have a graph that goes forever to the left, we skip 1, and then we go forever to the right. So that means our domain must be from negative infinity to 0. Actually not 0, I meant to say 1, so let's change that to 1. And we're going to use a parentheses because it doesn't include 1. We'll union that with another parentheses 1 to infinity. This is our domain from negative infinity to 1, not including 1, union 1, again, not including 1 to infinity. What is our range? Well, our range is everything that y can be. So if you look at our equation, y is equivalent to 5 divided by x minus 1. And this thing is simply a number that could be whatever it wants to be, except one value, and that's 0. If you look at the numerator cannot be equal to 0 because that's a constant number 5. And in the denominator, we can't have anything we want either. We can have negatives, we can have positives, but we cannot have a 0 in the denominator. So our range is also restricted. We can have a range from negative infinity to 0, union 0 to infinity. Again, this thing could be whatever it wants except 0, because in order to be 0, the numerator would have to be 0, and that is not possible. So our range is from negative infinity to 0, not including 0, union 0 to infinity, again, not including 0. A function f is defined with a rule or an equation using x and y for the independent and dependent variables. We say y is a function of x to emphasize that y depends on x. To use the notation y equals f of x, called function notation, to express this, and read f of x as f of x or f at x. The letter f is the name given to this function. For example, y equals 3x minus 5. We can also name the function f and write it down as f of x equals 3x minus 5. This is just another way to express our function f of x equals 3x minus 5 is very similar to y equals 3x minus 5. In example 6, let f of x be equal to negative x squared plus 5x minus 3 and g of x be equal to 2x plus 3. Find each of the following. In part A, we want to find f of 2. So usually we'll write f of 2 first, then we'll put an equal sign. And what are we doing here? We're going to plug in a 2 every single place we see an x for the f function. So this is negative 2 squared plus 5 times 2 minus 3. Again, every single place we see an x, we're going to replace those with parentheses. There was a negative in the front, so make sure you bring that down. We'll do our exponents first. Negative 2 squared, that gives me a negative 4. The 2 only affects the 2 and not the negative, and that's why it remains negative. We'll next do the product, 5 times 2, and that gives me 10. And now we have negative 4 plus 10 minus 3. These two together would give me positive 6. And finally, 6 minus 3, we get a 3. And that is our solution. F of 2 is equal to 3. Notice I line up all my equal signs. And I only write f of 2 once. We don't need to write it multiple times. For part B, we're looking for f of q. F of q just means we're going to replace everywhere we see an x with a q. So in this case, we'll write f of q first. And then I'm going to do substitution with the letter q into my function f. Alright, negative q squared. Well, the q squared just gives us a q with the negative in the front. I can multiply 5 times q to get 5q and just drop down that negative 3. Since there's no like terms, this is it. We are done with this problem. Our answer is negative q squared plus 5q minus 3. Part C, we want to evaluate this at g of a plus 1. That means I'm going to take a plus 1 and plug it into the function g. G of x is 2x plus 3. Since g of x is 2x plus 3, I'm just going to substitute that a plus 1 into the x. So you should write g of a plus 1 first to let the person know what you're substituting in, and then we'll plug in the a plus 1 into our function. We have 2 times the quantity, a plus 1 plus 3. So that means I need to distribute first. This is 2a plus 2, and then we'll drop down that 3. We'll collect like terms, and that means 2a plus 5, since 2 plus 3 is 5. And again, notice that I wrote g of a plus 1 once, and then I line up my equal signs until I reach the end. Example 7, let's find f of 3. This means that the x is going to be replaced by 3. So we'll write f of 3 first, and this is just a substitution problem. So we have 3 times 3 minus 7, and that means we will do the product first. That gives us 9. Drop down that negative 7, 9 minus 7 gives me a positive 2. And that completes part A. F of 3 is just 2. For part B, we know that f of 3 means that the x is 3. So the question is, what's the output? If I look at this function, there's only one where the input is 3, and that is this 0.3 comma 1. So the 0.3 comma 1 implies that f of 3 is equal to 1. That is our output where we're looking for the y coordinate. So f of 3 is 1. For part C, it's a very similar concept. F of 3, again, the x is R3. Where does it get mapped to? In this case, it gets mapped to 5. F of 3 is simply 5. For part D, I'm looking for f of 3 again. So we'll find the x is equal to 3. And I need to figure out what the y is. So if I look at my graph, the point 3 comma 4 is on the graph. This is our x, this is our y. That means f of 3 is 4. Again, the point x comma y is input output. R3 is the input and R4 is the output. Increasing, decreasing, and constant functions. Suppose a function f is defined over an open interval I, and x sub 1 and x sub 2 are in I. F increases on I if, whenever x sub 1 is less than x sub 2, f of x sub 1 is also less than f of x sub 2. Essentially, in part A, we're saying if you have a function x sub 1 is less than that of x sub 2, it's called increasing if f of x sub 1 is smaller than that of f of x sub 2. So as we go to the right, the function is increasing because f of x sub 2 is larger than that of f of x sub 1. Our function rises as we go to the right. Part B, f decreases on let me try it again. Part B, f decreases on I if whenever x sub 1 is less than x sub 2, f of x sub 1 is greater than that of f of x sub 2. Essentially what we're saying here is a function is considered decreasing if, as we go to the right, our function values, f of x sub 1 gets smaller as we go to the right. So f of x sub 1 would be greater than that of f of x sub 2. As we go to the right, the function decreases in height. Part C, f is a constant function on I if for every x sub 1 and x sub 2, we have f of x sub 1 equals f of x sub 2. This one's the easiest one to understand. Essentially, we're saying that at x sub 1 and x sub 2, the function has exactly the same height. F of x sub 1 and f of x sub 2 have exactly the same height. It's constant. The height does not change. Example 8. Determine the largest open intervals of the domain for which the function is increasing, decreasing, or constant. Notice in the directions we want open intervals. That means we're going to have parentheses on the left or right side of our intervals. The domain refers to x values. So we want to consider x values for which the function is decreasing, increasing, or constant. Notice as we head to the right, the graph falls to the point -2, -1. And since we're considering the domain, we're looking at the x. So the decreasing interval is from -infinity to -2. Again, this is an open interval, so we do not include the -2. If we continue to the right, the graph rises to the point 1, 8. And so it's increasing on the open interval from -2 to +1. Again, we have open intervals here, so we do not use square brackets. It is a constant function from 1, 8 and beyond, so our constant interval is from 1 to infinity. Example 9, this graph shows the relationship between the height of a kite in feet h of t and the time in minutes t. By looking at this graph of the function, we can answer questions about the height of the kite at various times. For example, at time 0, the kite is on the ground. The height then increases, decreases, increases again, and becomes constant. Then the kite returns to the ground. Use the graph to respond to the following. So we have the picture of the graph. We start off there at the ground, and it rises, it decreases again, and then it gets constant for a few seconds, and then it goes back down to the ground. Let's answer some questions. What is the maximum height of the kite? When is the maximum height reached? So we look at the graph here. We have the maximum height is at this point, and we can trace it down here. So the maximum height is at, it looks like 175 feet. So the maximum is 175 feet, and we reach that height in about 5 minutes. So let's answer that question. We have a max of 175 feet at 5 minutes. Part B, after the kite reaches its maximum height, does it begin to fall? What is the kite's minimum height as shown on the graph between 5 and 15 minutes? When does this minimum occur? If we go back to the image, the kite does begin to fall, and it reaches a minimum height right here at 10 minutes, and that minimum height is approximately 125 feet. The minimum is approximately 125 feet at about 10 minutes into the flight of this kite. When is the height of the kite increasing, decreasing, or constant? In part C, well, it's going to be increasing from 0 to 5 as it rises as we head to the right. So it's increasing from 0 to 5 minutes. Increasing from 0 to 5 minutes. It starts decreasing again from 5 to 10 minutes. And if we go back to the image, it's starting to increase from 10 to 15 minutes. Decreasing again. Actually, it's actually constant here. It's constant for 15 to 20 minutes. So we'll put that down. It's constant from 15 to 20 minutes. And then it starts decreasing again. Let's see where it decreases. From 20 minutes to 25 minutes, it starts decreasing. And that looks like all the parts we need for part C. It's increasing from 0 to 5 minutes, 10 to 15 minutes, decreasing from 5 to 10, and 20 to 25, and it's constant only from 15 to 20 minutes. Describe the height changes indicated by the graph. We'll do this verbally. It looks like the kite increases in height to 175 feet from 0 to 5 minutes. After that, it decreases to 125 feet from 5 to 10 minutes. After that, it increases back to 150 feet where it's constant for 5 minutes from 15 to 20 minutes. And then finally, it goes from 150 feet all the way to 0 feet to the ground, where it finishes off at 25 minutes.